Okay, I can see. I can see there are 53 participants. Let others come and join. I hope I am audible. Hello.
Yes,
Yes,
sir.
You,
sir.
yeah, you can clearly listen to me, right?
Yes, sir.
Okay. So I was discussing about the International Space Station. It is there in the space, and it needs constant correction in its position, its motion. And when there is something which is in space and it is having its own motion, and then the trajectory of the motion needs to be corrected. Okay, so that correction, so who can correct the motion? How you can correct a motion of some object which is there in space? Any idea? Any idea? Anything you can correct its position means you have to push it in some direction, or if you have to rotate it in some direction. Okay, so how will you do that? Any arrangement you just suggest me,
Typically,
anything.
some velocity might be given through the means of engines.
You can give velocity through jet engines, right? That's what you are. What happens in the international space we give it from out. Okay, if we use this technology, not this technology, this principle, balance of angular momentum. Suppose there are heavy flywheels are there in the station, very heavy flywheels. Start a motor and no issue. There is no uh, switch on the motor, and now suppose this axis of spinning, if you rotate it suppose in this direction, what will happen? There should be some moment there which should be applied in this direction to balance this. Okay, now you know it is in the space, so there is no one from outside which can apply this moment. In that situation, what will happen? We have already discussed what will happen. Suppose the flywheel in the space station is rotating in this direction, and with another arrangement you have given a rotation to this axis in this direction. What will happen then to this whole system? Because there is no one to apply this external moment. No one is there to apply this external moment. What will happen? I'm saying that this is taking a turn in this direction. So it is like this. The angular momentum vector is like this. It is taking a turn in this direction. That means the rate of change is in this direction. So the applied moment direction must be like this, but there is no one to apply this moment. That means this portion should go up or down. Hello, are you getting my voice?
Yes, sir, we are getting.
Yes, sir.
So, do you have the answer? Whatever I have asked you, I am saying that this is the this is the direction. So suppose the wheel is rotating in this direction, that means the angular momentum vector is this. And we are saying the whole thing we are trying to rotate in this direction. That means the whole thing we are trying to rotate in this direction. The essay. Okay. So in that case, the angular momentum vector is having a rotation, and the new position of the angular momentum vector is this. What is the change? This is the change. So this must be the direction of applied moment. If you look from the top, so this must be the direction of applied moment. That means if we see from this diagram, that means the moment applied moment direction is negative x direction. Is it clear? Hello, is it clear? In this case, the applied moment direction is negative x direction. If the wheel is rotating in this direction, and then the whole system we have rotated in that direction along this particle axis, we have rotated it in this direction, or you say we are taking a left turn. Okay, when you take a left turn, you see from this diagram that the moment must be applied along the negative x direction. Okay, but there is no one to apply that moment. All right, there is no one to apply that moment. That means if you do not apply that moment, which which should balance the system, then what will happen? Then this part will go up, this part will go down, this portion will go down, this portion will go up. That is a kind of moment we have applied due to this this motion. So there are heavy flywheels in the International Space Station, whose axes can be rotated, and the position or the motion can be corrected. Okay. We also have discussed this motion of this aeroplane yesterday. Suppose there are heavy so suppose there are one or two jet engines per wing, and all the jet engines are rotating in the same direction. We can consider there is one heavy jet engine which is rotating in this direction. And then same question. And then suppose the aeroplane is taking this turn, aeroplane taking the left turn. In that case, the angular momentum vector is taking this turn. So what is the direction of change in angular momentum? This is the direction of change in angular momentum. In that case, the external applied moment must be applied along this direction. That means if you just use the right hand screw rule, then if there is a moment that direction is like this, in the absence of that moment, because really there is no one to apply that moment, so what will happen? This front portion will go up. Is it fine? Hello?
Yes, sir.
Yes, sir.
So with this similar argument, suppose there is a ship. The ship is also having a very big rotational components. Those rotational components generally align their axis. This is the rotational components which I have shown for this ship. Uh, to show you differently, so I have drawn this as bigger than the ship. But just to show you that there are some rotational part which rotate in this direction. The axis of rotation is the axis of the ship. Okay, now the ship can have three kinds of motion. One is rolling. Rolling means it can roll about this axis. The ship can steer, it can go, it can turn left, it can turn right, and there is another motion which is called pitching. Okay, pitching means this bow goes up or down. Okay, that is called pitching. Okay, and the axis in this case we have shown this is the z axis, because in our formulation of the moment equation, always we have taken the axis of spin is the z axis, small z axis, and this axis we are taking, this is y axis, which is the vertical axis, and this is the x axis. We will study now. Suppose the ship is having any of this motion, then what will happen to the ship to balance the angular momentum? Okay, so let us first check rolling. If the ship is having this rolling motion about this axis, it can roll in one direction to another direction, it can roll. Okay, in that case, do you expect any gyroscopic motion if the ship is rolling about this axis? Because you see, this is the rotational, whatever, maybe this is a flywheel, maybe. Okay, the rotational component which is rotating, and it is rotating about this axis, which is z axis. So from our previous discussion, we know the direction of angular momentum is this only. Because suppose there is this rotation is there. So from the expression of angular momentum, that is I into omega, only component is along z direction. That means you have only the angular momentum component is along z direction only. Okay. In that case, on top of that, you are having the rolling motion. The rolling motion, with the rolling motion, what is happening? The angular momentum vector itself is rotating about its own axis. Okay, that means the angular momentum vector is not having any rotation about any other axis. So the change, the as we have seen for these cases, suppose it is like you increase or decrease the speed, right? Rolling means, suppose it is the whole ship is rotating in this direction. Okay, what will happen? So the phi dot will just increase, or it is rotating in this direction. The phi dot will decrease. In that case, there is no change in direction for the angular momentum vector. Okay, so if there is no change in angular momentum vector, that means there is no applied moment in other direction, or for this case in the x direction there is no applied moment. So for rolling, it has no gyroscopic effect. But when you consider steering, okay, you consider steering means the ship takes left turn or right turn. Okay, when it takes left turn, what happens? So I have made a table here to just check what will happen to this ship motion. You can make this table. So first column I have written, it is operation, then sense of rotation. Then I have written here change in angular momentum. And then we have written what is the direction of externally applied moment. Then what is the effect? Here we have written what is the effect. So for steering, suppose it is taking left turn. Now here I have just drawn the z-axis and x-axis. You are looking from the top. Okay, this ship, you look from the top. So for top view, you will see this x-axis and this z-axis. Y-axis is just this point. Okay. For simplified analysis, I have done so. This is the x-axis and this is the z-axis. Now, what is the angular momentum vector? It is along z-axis. That's what we have drawn here. Along z-axis. This is the angular momentum vector. Now, the ship is taking a left turn. If the ship is taking left turn, so for a small instant, this angular momentum vector will come to this position, right? This position. This is new position of the angular momentum vector. That means what is the change? This is the change. And this direction is what? This is the applied moment direction. This direction is negative x direction. So the externally applied moment should be mx should be in the negative x direction. If it is in the negative x direction, there should be a moment applied. Now the ship is in the sea. There is, and the water, you cannot resist the shear force. Okay, so it can go down, go up. So now there is, what I am trying to say is, there is no one to apply this external moment. In that case, what will happen? In that case, suppose this is the direction, negative x direction is the direction of applied moment. Okay, so that means there should be a force, like the on the bow it is acting downward, on this back side it is acting upward. That kind of a force should be applied there, which can create this moment about negative x-axis, right? But that kind of force is not there, which can uh, there should be a force which is acting downward here at the bow, and at the back side it is acting upward. Then only this moment can be created, right? But there is no one to apply that force. If that force is not applied, obviously the bow will go up. Do you understand this? Hello?
Sir, can you please repeat why
Yes.
the bow work?
Yeah, again I am saying that just look look from the top. Okay, you have learned how to draw top view of a system, right? So if you just draw the top view of this x axis, y axis and z axis, it will look like this. Do you agree with this?
Yes, sir.
Yes.
Okay, now this is the direction of angular momentum. Do you agree with this? This one.
Yes, sir.
Yes, sir.
Yes, sir.
And if you take a left turn, the change in angular momentum is this red one. Do you agree with this?
Yes, sir.
Yes,
So
sir.
the mx is in the negative x direction. This much you understand? Mx is in the negative x direction because
Um, MX is change in the two angular momentum.
yeah, mx is the change in angular momentum. I have written mx because it is in the x direction but in opposite x direction.
Okay, sir.
Agreed?
Yes, sir.
Is this fine? Now imagine how suppose you take two forces and you want to create this moment. How will you apply these two forces to create this moment? Two same forces, let's say F, two forces F, and you want to create this moment. कैसे करना है? So that force multiplied with the distance. No? So
Yes, sir.
Yes, sir.
you want to apply the force here downward, and same force upward. That force multiplied with this distance must produce this moment, right? Hello?
Yes, sir.
So now I am saying that who is there to put that force? That force, ये यहाँ पे जो इतना force लगाना है, is there anybody who is applying that force? Nobody is there applying, who is applying that force. So since that force is not there, what should be the effect? This bow will go up, right? Suppose somebody want to come to enter into your room, okay? Your door is there to stop, right? But somehow your door is open. Can you stop that person to enter into your room? You cannot. So that's what happening here. Bow will not go up if there is a force acting downward. But there is no force, no external force acting here. Hawaii hawa hai. It cannot stop the bow to go up. Is it clear now? If you have
Yes, sir.
understood this one, and to create this moment, nobody is there. So bow will go up. Now, now just look at the situation if the ship takes a right turn. If the ship takes a right turn, this is the angular velocity, angular momentum vector, then angular momentum vector will be at next instant will be like this because it is taking a right turn. So the applied moment direction is this, which is positive x direction. In this case, again, you see nobody to create this positive moment. So what will happen to the ship? Whatever written here is correct or not?
Correct, sir.
Yes, sir.
Now,
Correct.
okay, now we go to this case, pitching. Pitching means sometimes there is a operation where you want to rotate this whole ship about this x-axis, which is called pitching. You want to make the bow up and this backside down or backside up, bow down. This kind of motion sometimes necessary. To do that, some kind of arrangement is there which can do that. But when you do that, what is happening? This is the angular momentum vector. Okay, that angular momentum vector either going up or going down. Okay, that is again having a rotation. What kind of rotation? Now in this case, to make the analysis simple, now you see from this side, just from x direction, you are here looking to the ship. So what are the axes you will see? Y axis and z axis, right? Okay. So we have drawn this y-axis and z-axis. Now suppose you want a operation raise the bow. Okay. So the front portion go up. This operation you want. So what will happen? Angular momentum vector you just see. Angular momentum vector is here and you want to go the bow up. So the new angular momentum vector position is this. What is the change? This is the change. What is the direction of change? Minus y direction. So that means the applied moment direction is along minus y, the negative y direction. Now you tell me with what will happen to the bow if this moment is not applied. Please just see along the y direction. If you want to create a moment along this negative y direction, okay, what you need to do? There should be some force, horizontal force, pushing the back from the plane to us, or there should be some force which is pushing this bow from us to the plane of this drawing, right? That is how you can create a moment in the negative y direction. Yes or no?
So there will be force on the bow from left to right.
There will be a force on the bow
From from left to right means
yeah,
towards the paper.
from left to right, right? So, but there is no one to apply that force. Then what will happen? From left to right, not from this side to the board, right?
Yes, sir.
Negative y direction, because this is the positive y direction. Negative y direction is this. Always use the right hand screw rule. Then you will just use your hand, right hand screw rule. You will see that there should be a force from us to the plane of the board, right? Into the board. That kind of force should be there. But that force is not there. That means the ship had to take a turn in which direction? In the right turn. Similarly, Similarly, if you want the bow down, then you see that this is the angular momentum vector. It should go down. That means the change in angular momentum vector is this. What is this direction? This direction is positive y direction. Okay. So positive, in the positive y direction, there should be a moment, but there is no one to create that moment. That is why the bow, the ship will take a left turn for this kind of operation. Okay, have you understood this? I'll give you this
Yes, sir.
note. You just need to do one thing, that you just first understand. If you have understood this part from this one to this one, then you have understood everything. Rest is you just have to practice it. Okay. You want me to repeat it? Hello.
Sir, sir,
I'm
can
not
you
getting your
provide some ways to practice the questions?
Can you repeat it? I am not getting your voice. Hello.
Sorry, sir, network issues.
This PDF, just read it, and then if you do not understand anything, then let me know. I will go to the next topic. Next topic I have written here. Here we want to learn about the term which is called gyroscopic reaction. What is called gyroscopic reaction? You just consider this example. Here we have a shaft. On that shaft, a wheel is there. Let's say this is a flywheel, and that flywheel rotates in this direction. Yes, and the velocity is phi dot. Okay, we define this axis as z axis. Okay, and this axis, the vertical axis, is y axis, and this horizontal axis, this axis is sorry, x axis. So y and z, these three axes are mutually orthogonal, and they are following the right hand screw rule. Fine, no issue. Now I'm saying that this shaft is supported by two bearings. Here there is a bearing, here there is another bearing, and these two bearing are part of this structure. Okay, this structure, and that structure is on another shaft which can rotate about this y-axis in this direction. Okay, so actually we have a system where there is a there is an axis of uh, flywheel. This flywheel is rotating about this axis, and we have made a arrangement such that the axis of the flywheel can also have a rotation. We have already seen this kind of situation when there are two rotations. One is the rotation of the object, and then rotation of the axis about which this object is rotating. In that case, what will happen? The angular momentum vector is rotating. Since the angular momentum vector is rotating, it is having some change, and that change direction always gives us the direction for externally applied moment. In this case, you see that this wheel is supported by this bearing, this whole structure, and this whole structure is rotating about this y-axis. Okay, then what will happen? How the external moments will apply on this shaft? Simple. You just see that this is the direction of angular momentum vector, and it is rotating in the positive y direction. So obviously the rate of change in this direction along x-axis. Okay, if the axis of rotation is z-axis and axis of precision is y-axis, then obviously the applied moment direction is x-axis, right? So in this case, the moment which is applied on this shaft along the x-axis, and that can be created by these two forces. Are you agree? Do you agree with me? With these two forces, this is F and this is F, multiply F multiplied with this distance L, FL gives you mx, and which that mx is nothing but I into psi dot phi dot, the expression for mx. Do you agree with this expression?
Yes, sir.
So
Yes, sir.
then from here, if you know what is the moment of inertia of the flywheel, if you know what is the precessional velocity, if you know what is the spin velocity, then you know this whole thing. Also, if this distance between two bearings are known to you, then this is known to you, then you know what is the force F applied here, okay, on the shaft. This is the free body diagram of the shaft and wheel. Now, what is the free body diagram of the bearings? So there is a bearing here and there is a bearing. Okay, there are two bearings, and in these two bearings, if you draw the free body diagram of the bearings, then there is a force. So this force acting on the shaft by the bearing. So there will be another force which is acting on the bearing by the shaft. That force is just equal and opposite of this, right? That's what we have shown here. The reaction from the shaft on the bearing, the force is just opposite in this direction. We are writing here minus F because this is, we have written F, so minus F. You cannot, means you understand that this is the direction and the magnitude of the force is F. Obviously, here you have another bearing which is supporting, and that bearing, what is the force applied by the shaft on the bearing? This is the force, right, in the opposite direction of this. Do you agree with this drawing? Hello. So this reaction which is given by the shaft on the bearing is called gyroscopic reaction. In general, suppose this rotation about this axis is not there, when you design the bearing, you will just design for its static load, right? Whatever static load is there for that, and the rotational thing, due to that, whatever forces require, you will design the bearing for that. But if this axis is also having some precision, as it is there in this case, in that case your bearing will have extra forces, extra reactions due to this gyroscopic motion. You must consider this. For example, you just consider in the classroom you have seen there are many fans which are wall hang fans. Those wall hang fans can swing, right? So fans are rotating about its own axis. The blades are rotating about its own axis, and then the whole head is having some swing. Due to this swing, the angular velocity, angular momentum vector is also having some rotation. Okay, that rotation will create some gyroscopic reaction to the bearings. When you design the bearing of this fan, you must understand, you must take care of this gyroscopic reaction. I hope you have understood this gyroscopic reaction. Is it clear? Do you have some idea about now about this gyroscopic reaction? Hello?
Yes.
Yes, sir.
Okay, let's go to next topic. The next topic is another interesting topic, which is the stability of a two-wheeled vehicle. All of you have experience of riding bicycle or motorbikes, right?
Yes, sir.
And these two-wheeled vehicles, they are not stable. If you just keep it, do not run it, and if you just keep it vertical, will it be there? It will fall down,
No,
right? It will fall down. If you have a coin just with you, try to make it vertical. Will it be there? It will fall down, right? You just take a coin. 5 रुपए वाला कॉइन लेने से नहीं होगा, वो तो खड़ा रह सकता है. 1 रुपए वाला कॉइन ले लो, 10 रुपए वाला कॉइन ले लो. If you just make it vertical, will it stay there on the table? It will fall down. But just try to roll it on the table. It will not fall. Well, it will fall after some time. Is it not?
Yes, sir.
Why is it so? Have you asked this question to yourself? Why is it so? Now, this angular momentum balance will give you the answer. Why is it so? Why it is not? So we in our childhood we have played with tires. How many of you have played with tires? The cycle tires or motorcycle tires. You just run it on the road. कितने लोग ये खेल खेल चुके हो?
yes,
When
sir.
you keep the
Yes, sir.
when you keep
Yes,
it,
sir.
when you
Yes,
keep
sir.
it on the road static position, it will not stay, it will fall down, right? In the vertical position, when you keep the tire, it will fall down. But if you run it, if you roll it on the road, it will roll, it will not fall down. This experience you have, or many of you have this experience, right?
Yes,
So
sir.
why it is the question is why it is not falling down? It is due to the gyroscopic motion, this balance of angular momentum. So all of these questions we will answer or will understand through this topic, stability of a two-wheeled vehicle. So suppose this is a bicycle. This bicycle is running on this path, and you taking a turn. Okay, so if we are looking from this side and it is taking a turn, and a simplified figure we want to draw for the rotating components only, for this wheel and this wheel. We have just drawn one wheel, okay, here, and you are looking from this side. Generally what happens, you take we when it is taking a turn, you will see that when you are riding a bicycle or motorbike, you taking a turn, you have some kind of heel. Your position is not actually vertical. Some kind of angular inclination is there from the vertical. Do you agree with this?
Yes, sir.
So that position is drawn here. Suppose this is the tire or this is the wheel. Okay, we are looking from this side. How the wheel will look like? It will look like this. Okay, this is the wheel. This is the ground where it is touching on the ground. Okay, this is the point where it is touching the ground, and you have, this is not exactly vertical, some angular inclination is there. We designate this angular inclination theta. In actual case, this angle is not this big, it is very small. But for our analysis, for our understanding, we have drawn this big angle here. This angle is theta. This angle is called angle of heel. Okay. Now let us write down, associate some axis with this. Since this cycle is running and it is taking turn, wheels are rotating in this direction. Okay, wheels are rotating in this direction. Here we have, so it is coming from this side and we are looking from this side. That means the wheel is here, its rotational axis is this axis. Okay, this is the z axis, which is its rotational axis. Do you understand this point? This is the z axis, which is the axis of spin for this wheel. Do you understand this point?
Yes,
I
sir.
need I need some feedback. Without that, I cannot move forward. So this is the wheel, which is, just imagine the cycle is coming this way. Okay, we are here. We are looking from this side. That means it has this wheels are having this rotation. So the z-axis, we are saying from here. This is the z-axis. So that z-axis is there. Okay, we associate another axis, which is the y-axis. That axis is along this direction, the okay, along the plane of the wheel. This is the y-axis, and this axis, which is horizontal, is x-axis. Just understand these three axes. Then we will come to we'll go to next step. If you are convinced with these three axes, then we will go to next step. We have taken one axis which is along this direction, that is y-axis. The wheel is spinning around this axis, that is z-axis, and this, from this point, center of the wheel, we have drawn a horizontal axis, that is x-axis. Are you convinced with these three axes that this can be a coordinate system, x, y, and z? Is it fine? Small x, small y, and small z. Is it fine?
Yes, sir.
Yes, sir.
Okay. Now you see this cycle is taking a turn like this. That means the whatever motion is here, this rotational axis, for this case, suppose there is, when there is no heel, that is horizontal, and when it is taking this turn, that axis of spin, that is also taking a turn, right? And that turning direction is this direction. Here we have shown, that is this capital Z direction. Okay, this is the capital Z direction. About the capital Z direction, this turning is taking place, right? The wheel is following a path like this. So that means it is taking a turn about the vertical axis, Z axis. Okay, now from our previous discussions, in this discussion, previous discussions, what we have, this is the axis of spin. This is the this is the axis of applied moment, and this capital Z is the axis of precision. The angle between the vertical axis and this uh, axis of spin, this angle is theta. Okay, so similarly, let's see what is that angle here. That angle here is from the axis of precision, that is this z axis, because the turning taking place about this vertical axis, that is this capital Z axis, an axis of spin. What is this angle? This angle is 90° plus theta, right? Is it okay? The
Yes, sir.
Yes, sir.
axis of precision, axis of spin, their angle is 90° plus theta. So the expression of moment was this: we must substitute theta equals to 90° plus theta, because this theta is actually angle between the precisional axis and the axis of spin, and that angle here is 90° plus theta. So we substitute in place of theta, we are writing 90 degree plus theta. Don't be confused that this theta is the angle between the precessional axis and the axis of spin. It is not so here. Okay, you can take another angle A, B, C, D, whatever may be, but this angle is the angle between the precessional axis and the spin axis, and that angle is 90 degree plus theta. So we substitute it here, and finally the expression for moment along x-axis, you get the expression like this. Now this I minus I0, we have discussed yesterday also in our last class, that this I minus I0 is small, okay, and this sine theta, if theta, as I said, that this theta is very small, this theta is very small, so small that you don't realize when you are running on the road. Okay, every time you are having this kind of motion, very small turn and very small for stability, very small turns. Now sometimes you will see when you are having a slow cycle race, then you realize this slow cycle race is difficult than the fast cycle race. Why? Because here the answer you will get. So what I am saying, that this angle of heel is very small, and this quantity is again smaller quantity. So when you multiply two smaller quantities, it is very small compared to this quantity. Okay, that is why in the next expression what we will do, we will approximate this is equals to 0. And the expression of moment we will have this. If you refer to uh, some books, they directly write down this expression as the component of angular momentum, sorry, as a component of moment in x direction, but those expressions are not correct, incorrect. Okay, so those books, if you follow, if you will have wrong notion, you will have wrong concept. So I will request you to just follow the way we have developed the uh, whole thing, expressions, equations we have developed, and step by step I have introduced why this expression is so. Okay, mx equals to I theta dot psi dot cos theta. This is the expression for externally applied moment for this case. Now, since there are three wheels, you can see two, the front wheel, the back wheel. If it is a bike, there is some flywheel in the engine or rotating parts in the engine. So all of them will have some angular momentum, and all of them, since taking this turn, all of them will have some gyroscopic effect. So this gyroscopic moment should be there for all three wheels. Okay. Now in this case, we change some notation. The psi dot we are writing omega p. This is called velocity of precision. Okay. Phi dot we are writing omega w. There are two phi dots because in this case we assume that the radius of front wheel and back wheel are the same radius, so their speed also same, and that speed we are calling omega w, omega wheel. And phi dot of engine, the spin velocity of the engine, we are calling omega e. Okay, so the gyroscopic couple has three components. These three components are related to rear wheel, front wheel, and engine. Okay, so and suppose the moment of inertia of the wheel is Iw, moment of inertia of the engine is Ie, then total gyroscopic couple is the addition of these three components for the rear wheel, for the front wheel, for the engine. So the expression is mx का expression क्या है? I theta phi dot psi dot cos theta. Okay, phi dot psi dot cos theta. So I omega w omega p cos theta. I omega w omega p cos theta. This is rear wheel, front wheel, and this is the expression for engine. IE means moment of inertia of the engine rotating components. Moment of this is the angular velocity of the rotating components in the engine, and this is common to all. This is the precisional velocity because the whole system is taking this turn with this angular velocity omega p. Okay, so with this we have, this is the expression for gyroscopic couple. But now we have to see what is the expression, what is this mx, what is the externally applied moment. So to do that, we have drawn the free body diagram of this system, this wheel, a little bit simpler here. We have drawn it here. So suppose this is the wheel which is touching ground at this point, and this height is this radius of the wheel in this case is h. Radius of the wheel is h. This angle of heel is theta. Now since this is taking, the whole thing is taking a turn, and this precessional velocity omega p, that means there is a centrifugal force acting on it, and that centrifugal force is the total mass of the wheels omega p square, which is the precessional angular velocity, its square, multiplied with r, the rotational the radius of rotation. Okay, suppose this is the turning it is taking. So whatever may be the center of this circle, from that point to this point, the radius we have to take, and that radius we are saying that is equals to this capital R. So mr omega square, or in this case what I have written uh, here. Here we have written m omega p square r. That is the centrifugal force which is acting on the center of the wheels. And then since it is no more vertical, so there is the mass, from the mass center, the weight is acting downward. Okay, so these are the two forces which are acting on the center. Due to these two forces, that will create a moment about this point on which the wheel is standing on the ground. Okay, so if you take moment, then that means this omega m omega p square r into this distance, which is h cos theta. Okay, and that is creating a moment along the x-axis. On the other hand, mg into h sine theta, okay, that is creating, sorry, this will create a moment along the x-axis, but this will create a moment along negative x-axis. Okay, so that's what we have written here, mgh sine theta, okay, which is the moment due to this weight, and m omega p square r into h cos theta, which is the moment due to centrifugal force, but that is in negative direction. So this is the total externally applied moment, and that must be equal to this. And we will make it equal from here, whatever, since this is only one equation, you can find out one unknown. So if you want to just find out what is this theta, all other things are known to you, you can find out that. Some of the things we must note here. Suppose the velocity of the vehicle is v. Okay, can we find out what is the precessional angular velocity? If the radius is given, what is the radius of the rotation that is given, from that we can find out. Am I audible? Still audible? You are there in the class? I'm having some
Yes, sir.
Ye-
Audible.
Yes,
phone
sir.
calls.
Yes.
Yes, sir.
Okay. We'll take 5 more minutes to finish this class. Okay. So v is the velocity of the vehicle. R is the radius through which it is taking the turn. That means if you just multiply the precessional angular velocity and r, you will get the velocity of the vehicle, right? Are you fine with this expression? Suppose the cycle is taking a turn like this. ऐसे यहाँ से ऐसे turn कर रहा है, and the radius is known to you. So what is this precessional angular velocity? R into omega p at any point must be the velocity of the vehicle. Agreed? If so, then you can find out omega p equals to V by R. On the other hand, sometimes the gear ratios are given. So that means the speed of the engine and speed of the wheel. There is a gear uh, in between, there is a gear system. So there will be gear ratio. So if that gear ratio is given, then you just know the wheel speed. So you know the engine speed. Okay. The wheel speed and engine speed are known to you. Now, also the vehicle speed is known to you. So at any point of time, if you just have the radius of the vehicle multiplied with its uh, angular speed, that gives you the speed of the speed of the vehicle is equals to angular speed of the wheel multiplied with the radius. That means if this v is given, you can find v is given and the radius of the wheel is given, you can find out what is the uh, angular velocity of the wheel. Once you know the angular velocity of the wheel, this gear ratio is given, you can find out what is the angular velocity of the engine. Okay. Now this is an example of a motorcycle which is taking a turn, and we need to determine the angle of heel. Total mass is 180 kg. The moment of inertia of the wheel is 1.2 kg meter square. Radius of the wheels, it is given r equals to 0.3 something. Moment of inertia of the rotating parts of the engine is given by this. Radius of the turning r, that is also given. The velocity is given. Gear ratio is given. The height h is also given. Now we have to find out what is the heel, angle of heel. What do we need to do? We need to find out what is the gyroscopic couple. Already we have this expression here. This is 2 IW omega W plus IE omega E omega P cos theta. Okay, so we'll use that. Simple. This IW is given. V by R already we have discussed is the angular velocity of the wheel. And here this G, you see this G multiplied with the angular velocity of the wheel gives you the angular velocity of the rotating components of the engine. And this is the moment of inertia of the rotating components of engine multiplied with omega pk expression अभी हम लोगों ने निकाला है. And this is the expression. From this expression we have the gyroscopic couple is this. Now we need to find out what is the centrifugal couple and what is the couple due to weight of the wheels and engine. Okay, so that is the centrifugal couple is this m omega square r into h cos theta. So this m is given 180 kg totally weight of the engine, motorbike, everything. So using that we have this expression, and due to weight the couple is this much, and then we apply this balance equation. The externally applied moment is equals to this gyroscopic couple. Okay, so when you do that, you will have an expression like this. From that expression, you can have expression for tan theta. So theta is actually equals to, we got it is 36 degree. Okay, stop here. I will send you this PDFs so that you can follow it again. And next day we'll discuss about the stability of a four-wheel vehicle. If you have any doubt, you can ask me. And this weekend, I will give you 1 hour time so that you can come to me and personally and discuss. In some, I will sit in my office. You'll come to me and you can discuss if you have any doubt related to this. This is unfortunate that I cannot take the classes physically, but what can I do? I have to do like this. Okay, that's all. If you have any doubt, you can ask me right now. If you don't have any doubt, let me thank you for your patience. Tomorrow, I think
Thank you, sir.
8 a.m. The class is tomorrow 8 a.m. Okay. Next class tomorrow 8 a.m.
Okay, sir.
Okay.